So yeah, so the basic idea is group 2. They are called group 2 because they have 2 electrons in the last shell. We write it like that. We also call them earth metals, or sometimes just not earth metals, alkaline earth metals. Okay, that's something that we call them, alkaline earth metals. I'm not sure why we call them that. Must be some reason. We have these groups. These are beryllium, magnesium, calcium, strontium, barium, radium. Mm, the atomic size increases downwards. There are many other important qualities that they have. For example, their melting point, decreases downwards. They have low densities, so all of them have low density, relatively low melting point compared to transition metals, but of course more than the other metals like group 1 metals that we talked about. They have all are shiny. They all have silvery surface, and yeah, that is basically their physical properties. There, many of them are like brittle maybe, and they're kind of difficult to make into wires and all that. They're not that malleable. What they do have in common is that all of them, this is 1s2, this is 2s2, 1s2, and then 2s2. The last one is 4s2. In fact, calcium is 4s2, and this one is 3s2 all the way. This is 2s2 all the way. This says we don't have 1s2 in this group. 1s2 is helium. We don't have it here. Yeah, something that I kind of struggled with when I was studying it. That why don't we have helium in this group? It fits right in. Maybe someday I will make a group periodic table in which it will. 4s2, then 5s2, then 6s2, and obviously 7s2. Yeah, so it's pretty straightforward. The pattern is all of them have s2 in them, and that means that they all have this s block, which is completely filled up, and they're all in s block. Periodic table has these 4 blocks. So there is this. So periodic table has these 4 blocks. Students just have 1 block, the mental block. So SPDF, those are the blocks. So S is basically this one, and in this one we have group 1 and group 2, and the group 2 is where all of them have S. So the reason it's called S block is because the last shell, it's ending in S. That's why they're called like that. The melting point, it doesn't really show a clear pattern. For example, beryllium has, in fact, let's leave beryllium. Magnesium has around 649. I have a table here. I'll just copy that table. So you can see that magnesium has 650 almost. Then calcium has a higher, then strontium is suddenly down, and barium is suddenly further downwards. So they don't really have a clear pattern in their melting point. And same thing goes for their boiling points. So the boiling point increases from magnesium to calcium, then decreases, then increases again. There are a couple of reasons for this, but all of them are beyond our syllabus at the moment. So we don't really concern ourselves with that. Then we have ionization energy. That's something we should be able to explain. So magnesium to barium, there's a clear trend of decreasing ionization energy. The reason is straightforward. You're getting a bigger atom. The bigger atom means you have more shielding, less effective nuclear charge, and obviously it decreases the ionization energy. Atomic radius is also not on your side. Second, ionization energy again shows a similar trend. Again, for the same reasons, bigger atoms, which means the radius is increasing, effective nuclear charge is decreasing, and shielding effect is increasing. So because of all that, the atomic size, as you can see in the ionic radius thing, it's also increasing, which means that shells are going further and further away. So it takes less energy to remove the last 2 pairs of electrons, because they're technically the last shell. They are the 2 that comprise the whole last shell. So yeah, that is the main idea of these things. Their ionization energy, they have a downwards trend. It is quite downwards initially. Like if I were to graph them, here's a graph of second ionization energy. So by the way, can anybody write the equation for second ionization energy? What would it be? Let's suppose I want to write the second ionization energy of calcium. What should I do?
It would be calcium +1, and
Very
then
good.
you put an electron next to it. No, it will be calcium +2 and an electron.
Yeah, very good. But if this was in an exam, we would lose a mark. Why are we losing a mark?
So we have to write the gas symbol.
Very good, very good. Okay, if somebody says calcium changes to calcium 2 plus and 2 electrons, how's that wrong?
Because they don't happen together.
What do you mean?
Like it has to lose one electron at a time.
Exactly, exactly. The ionization energy in this one is embedded already. So this will take both ionization energies first and second together. So yeah, that's it. The thing is that ions of second thing is that ions of these atoms are much smaller than the atom. Can somebody give a reason why that is? The ion is much smaller than the atom. Why would that be?
So because now that it's like positively charged, like there are more protons than electrons, so they pull on them.
Okay,
with
that's
like a
one
greater
reason,
force.
but still, it doesn't explain the difference in their size. The difference is insane. It's too big. The reason is that they absolutely lose their last shell. So it has 2 electrons in the last shell. They lose 2 and they're gone. The whole shell is gone, which is why the ion is much smaller than the atom. It has technically lost a whole shell. That's why. All right, let's talk about their chemical properties. The first one is, how do they react with water? Now, because they're more reactive than hydrogen ion, they will displace hydrogen ion. But how they do that, how they go about it, is slightly different for different atoms. Thing is, down the groups, you know that they become more reactive, right? But even then, they're not as reactive as group one, because group one has just to lose 1 electron, and they're pretty good at it. But compared to them, group two has to lose 2 electrons. There's the first ionization energy, then the second ionization energy. The energy requirement is much greater, which is why their reactions are not as vigorous. But just like that, in group one downwards, atoms were becoming bigger, so reactivity was increasing. Same is the case here. Down the group, reactivity increases. So we don't study beryllium in O levels, just like we don't study lithium in OA levels. So, but magnesium, let's start with that. So magnesium, if you reacted with cold water, the reaction is going to be very slow. Okay, but you suddenly heat that thing up, you make it steam, then the reaction is much straightforward and very rapid. So doesn't really react fast with the cold water, but with steam it has the activation energy required, so it changes to magnesium oxide, releasing hydrogen gas. The reason it does that is because magnesium 2 positive ion is able to displace both the hydrogens from oxygen, now from water. But calcium, being the more reactive one, reacts with cold water. And when it reacts with water, it forms calcium hydroxide. Now, again, this is a two-step method. Basically, it forms calcium oxide just like magnesium, but then that calcium oxide forms a complex with water and forms calcium hydroxide. Calcium hydroxide is slightly soluble. Magnesium hydroxide is completely insoluble. And calcium hydroxide, that's why sometimes, for example, in your book, you will sometimes see this and sometimes you'll see this. Now, when you have calcium hydroxide solid, we call that slaked lime. But when you have it in aqueous form, we call it lime water. And I think you have heard of both of these terms, right? In O levels. So slaked lime is a solid that we put on soil to fix its pH. And lime water is something that we use to test carbon dioxide with. The reaction of barium will be along the same lines, and barium will produce barium hydroxide. And that will release hydrogen gas, and barium hydroxide is completely soluble. Okay, so does that give you a trend in their hydroxides? Is there a trend in their hydroxide?
They become more soluble down the group.
Very good. Down the group, they become more soluble. Exactly. So magnesium, it has a very slow reaction with water, produces hydroxide, hydrogen, like magnesium. I should write it down. Magnesium plus water, when it's liquid, produces magnesium hydroxide and hydrogen gas. We can balance it out later. It's just going to be this. Yeah. And the other ones, with steam, magnesium reacts to produce magnesium oxide. And that's the same with other things. For example, if I took calcium and I reacted with steam, the reaction is going to be really fast. A vigorous reaction, in fact. And it's going to produce calcium oxide and hydrogen with a very bright white flame. Barium will do the same thing. In fact, barium will explode with steam. Okay. Again, these things are white because they don't have transition metal in them. So you understand that with cold water, all of them produce hydroxides, and those hydroxides become more and more soluble down the group. But with steam, they all produce oxides, and those oxides uh, they start to explode as you go downwards because they have a lot of energy. Can you write an equation for strontium reacting with water when it is liquid and when strontium is reacting with water as a gas? Can you complete these equations? Okay, so strontium with water produces strontium hydroxide and hydrogen gas, but strontium with steam produces strontium oxide and hydrogen gas. This reaction is going to be quite vigorous over here, but it's going to be explosive over here because with steam, it's going to have a very high energy, and that's going to suddenly explode this thing. Okay, so that's the reaction with water. There's a clear trend. Down the group, hydroxides also dissolve. Why do they do that? Why do they dissolve? We'll study that in A2. Now with oxygen, how do these things react with oxygen? Again, when you're doing it with oxygen, you just have to heat it up or you have to burn it up, and that's oxidation. They all form oxides. Beryllium doesn't burn, but if it does, it's not as bright. But again, who's studying beryllium? Magnesium, calcium, barium. There should be enough. So magnesium with oxygen produces MgO. Calcium with oxygen produces calcium oxide, and barium with oxygen produces barium oxide. All of these are white solids, and they are all burning with some colorful flame. So for example, magnesium has a white flame, and it's really blindingly white. बहुत ज़्यादा white होता है. In fact, बहुत ज़्यादा खौफ आता है उसको देख के. But then you use this, जो आप fireworks में white color होता है ना, वो magnesium होता है. So वो बहुत bright होता है ना, तो इसलिए we use it in fireworks. Then calcium burns in red color, and that is why you can test if something has calcium by burning it. Okay, for example, your teeth or bones, they all have them. So if you burn them, but the calcium amount is really small. I think 0.0035 or something. I'm not sure. बहुत वक्त हो गया ये number याद किए हुए देखे थे. And then barium burns. Barium, I think, has a green flame. And then there is strontium. Strontium also burns, and strontium also has a color. I'll have to look it up. It is that color, crimson. Yep. We have to thank the crimson people for this Zoom call we're having that doesn't close after 40 minutes. Yeah, so it burns with a crimson flame. Okay, so you clearly see a trend there that they're all burning more and more vigorously, and they're all producing oxides. Okay, so that's their reaction with oxygen when they burn. Then we have reaction with acid. Again, pretty straightforward reaction, just like water. They're also going to react and produce water. Maybe they were producing hydroxide. Here they'll also produce salt with acid. So group 2 metal with acid, for example, calcium with HCl is going to produce calcium chloride and hydrogen gas. So that's how they do. Down the group reactivity increases, and all of these salts that they produce with acids are soluble. There's one exception. Do you remember which salt does not dissolve for group 2? Please call back. Call back kya hai? That's calcium and barium. Yes. So if you're reacting with them with sulfuric acid, so when it reacts with sulfuric acid, it produces calcium sulfate, which is insoluble, which is why the reaction does not go to completion. Hota ye hai that let's suppose you have sulfuric acid here and you have calcium. So calcium is going to react outside on the surface, obviously, and there's going to be a layer of calcium sulfate on the top, which will keep the particles inside from being exposed And that is why it wouldn't react completely. If you wanted to react to a greater extent, make a powder of it. So crush it so that you have a powder, and that powder, when you spread it out, it will create another powder, which is calcium sulfate. So these reactions on their own, if you have lumps of these metals, they will not go to completion. And there's a reason for it. Again, there's a reason why sulfates don't dissolve. It's a pretty interesting reason, because the same reason is there for why hydroxides dissolve, and same reason is why sulfates don't dissolve. And yeah, we'll study that in A2. I wish I could explain it to you, but right now we need to focus on this, and then we'll study, when we study bond Haber cycle, uske baad inshallah it will be much easier for you to understand why sulfates become insoluble down the group. And that's our first trend here, that sulfates become insoluble, but hydroxides become soluble down the group. So magnesium sulfate will be soluble, magnesium hydroxide is insoluble. Barium sulfate is insoluble, barium hydroxide is completely soluble. So they go opposite to each other. Again, what will you observe? You will observe that the metal starts to dissolve. Okay. Now, the oxides that they make, they're all basic. So their oxides are basic with very strong, high bonding. So they have high melting point, which is why they have really good uses wherever there is high temperature. For example, in the case of refractory lining for furnaces and all that, use magnesium oxide there. So how do you prepare them? It's pretty simple. You take there are two ways of preparing oxides. One is you take a hydroxides, for example, this thing, and you burn it. You heat it basically. You don't really burn it. Burning is reaction with oxygen. You're just heating it. When you heat it, it breaks down, gives us water and magnesium oxide. Okay. And one crude way of understanding why this works, technically wrong, but why this works is that the bond of magnesium with oxide is much more stronger than the bond of oxide with H. Okay. So, or the other oxide that you have. So what happens is that this goes away, forms water, and that is left over. Again, that's a crude understanding of this thing. Examine likhana. Okay. Yep. So that's how it works. That basically magnesium hydroxide is going to break down and produce magnesium oxide. Same thing happens with carbonate. Again, in carbonate, you have carbon dioxide loosely bonded to oxide. So when you're heating it up, magnesium oxide is made with carbon dioxide leaving it. So in the case of hydroxide, water is made. In the case of carbonate, carbon dioxide is made. And you're left with just the oxide. Okay, their oxides will show the same trend as hydroxides. So oxides and hydroxides become soluble down the group. And obviously, because they're basic, when they dissolve in water, for example, let's say barium oxide dissolves in water. What is going to be the pH of solution? It will be greater than 7. They're alkaline. Their oxides are basic. Carbonates don't dissolve. Okay, carbonates are insoluble. I think we already know that. So carbonates and phosphates, they're insoluble. They don't dissolve. Oh yes, thermal stability. Do you understand what that means? What does thermal stability means? It means, does the thing remain the way it is if you heat it? If it does, and you keep on increasing the heat, and it still does, it is very stable. But if you heat it and it breaks down, then it's not thermally stable. So we have a trend here. The carbonates are more thermally stable downwards. As you go down the group, thermal stability increases. They become more and more stable.
Sir, can you repeat what thermal stability is?
Thermal stability is that, for example, if I take calcium carbonate and I heat it, it's going to break down and produce calcium oxide and carbon dioxide. But if I do that with strontium carbonate or barium carbonate, then I heat it and it will not break down. So that means barium carbonate is more stable than calcium carbonate. In fact, they won't break down at the same temperature. Barium carbonate, if I want to break it down, I will have to heat it much more, so much more, to produce barium oxide and carbon dioxide. higher temperature is required. So that means it's able to withstand more heat. A temperature at which magnesium carbonate will break down, calcium carbonate might not. But calcium carbonate will break down at a temperature where barium carbonate won't. And barium carbonate can withstand higher temperatures even. Okay, so that's the thing. They're more stable as you go down. And that's not just carbonate, that's also with nitrates. Their nitrates, if you heat them, they will also break down. And there's an interesting equation there. So for example, if I take magnesium nitrate, I'm breaking it down, balance they break down and they give us, so as I was saying, the nitrates and carbonates, both of them break down the group and they produce gases. Carbonate produces carbon dioxide, nitrate produces nitrogen dioxide. So they have a very similar trend there. And down the group, they're going to become more and more stable. Okay, that's what they, and that's it. That is what group 2 are and things we need to know about group 2. So let's quickly go over the things. First of all, they're alkaline earth metals, which have basic oxides, and they have 2 electrons in the last shell. So they easily lose those 2. Their lattice is not that strong. So they have low density, low melting point. They don't have any trends in melting point. It's all over the place, increasing, decreasing, so on. Same for boiling point. Ionization energy instead decreases down the group, and that is because the atom is becoming bigger and bigger. So there's more shielding, less effective nuclear charge, greater radii. So that's there. The ionic radius is much smaller than the atomic radius because they basically end up losing the whole shell. There's a trend for ionization energies. They react with water. With cold water, they react slower than steam, obviously, and the reactivity increases down the group, which means that with cold water, magnesium will react very slowly and produce insoluble hydroxide. But with steam, it produces oxide. Same trends with calcium and barium. And down the group, their hydroxides become more soluble. In fact, the reactions become much faster later on. With oxygen, they burn and they burn with a brighter flame. And as you go down the group, the colors are going to change. So white, red, green, and crimson are the colors for magnesium, calcium, barium, and strontium. You need to remember the color for magnesium and calcium. Baki dono ka chahe aap abhi aap na bhi kare. They do react with acid just like they do react with water, that they're going to replace or displace hydrogen ion there. And they produce soluble salt with acids except sulfate. With sulfates, their solubilities decrease down the group. So they're more insoluble. With oxide and hydroxide, they are more soluble down the group. So it's the opposite way. The reason is still the same, but we don't have to get into that. Oxides that they have are basic, and their hydroxides can break down to produce those oxides. So can their carbonates. And carbonates and hydroxide both will break down when you heat them, depending on different temperatures. Their hydroxides become more soluble, as I just said, but their carbonates are completely insoluble in water. So same goes for their phosphates. When you heat them, nitrates and carbonates are going to break down, but oxides won't. Oxides are able to withstand very high temperatures, which is why we use them in furnaces and everything, basically places where there is a lot of temperature to withstand. Nitrates and carbonates will instead break down, and down the group, they become more and more stable, which means you need to give them more and more energy to break them. And when they break, the carbonates break down and give us carbon dioxide and oxide. And when nitrates break, they give us nitrogen dioxide, oxygen, and oxides. And those are the key points to remember for the AS level group 2. Now, do you know the use of calcium hydroxide and calcium carbonate in agriculture? For example, calcium hydroxide is used to increase soil pH, and so is calcium carbonate. Calcium carbonate is usually used in powdered form because carbonates are insoluble in water. So it's what I say. Yeah, that's it. Okay.